Hello and welcome back. Today we're talking about positional encoding. Let's have a look at this sentence. Horses eat apples. Now, if we move the words around a little bit, we'll get apples eat horses, which is a grammatically correct sentence with exactly the same words, but with a very different meaning. And this shows us that word order is very important when dealing with text in order to understand the meaning of a sentence. Now, previously, when the artificial intelligence community was mostly working with RNNs and LSTMs, word order was preserved by design because these types of models are sequential. But also, this was a drawback as well because sequential models are slow to train. And in any case, we're not dealing with RNNs and LSTMs in this series of tutorials. We're dealing with transformers. And here, even though this is not a transformer yet, we're building one up slowly and we'll get there very soon. But already we can see that transformers ingest the words in parallel, all at the same time. So even though for us we see horses eat apples, you see these words in a sequence, the transformer sees them as just three words: horses eat apples. And they can be in any sequence, doesn't know the sequence they're in. It doesn't have that mechanism for knowing the sequence of words. And this can, of course, lead to problems, as we could see from the examples above. So we need to give transformers a mechanism for knowing in which sequence the words came. And there are many ways of doing it. We're just going to jump straight to the solution. This is the approach that was used in the paper. And at the end of this tutorial, I'll provide a link to a blog post where you can read more about different methods of positional encoding. But we're just going to stick to this one and understand how it works. So here are our vectors. Horses eat apples. Each one is embedded with 500. Each word is embedded with a 512 dimensional vector, as we discussed previously. And now we're going to illustrate what is shown or what is expressed with this formula on the left. And what is expressed is these sine and cosine waves. So there we've got one pair. The next one is the period increases. Then we got the cosine wave. Then again, the period would increase, and then we have a cosine wave, and so on. So you get the picture. Like we keep building in these sine and cosine waves 512 times in total. Now we're not going to draw all of them for illustration purposes to keep things simple, but there are there. So there's 512 of them, and this is regardless of the size of the input sequence. And how are we going to encode our words? Well, for the first word, we're going to take a slice over here and at the very start, and we're going to see where this slice intercepts our waves. So these intercept points, they are going to be used as an encoding for position number 1. Position number 2, we're going to take a slice over here, and it's a bit to the right. It's expressed in the formula. It's always fixed where that slice is taken, and these are the encodings for position number 2. Position number 3 is encoded with these intercepts. Position number 4, position number 5, 6, 7, and so on for each word. So if you have 17 words, 17 times. If you have 1,000 words, whole paragraph, then 1,000 times. And as we can see, these positions, basically what we're doing is we're expressing the position of a word. So for example, word number 3, we're expressing this position through this series of numbers, this set of numbers. And this set number of numbers is always going to be fixed. Always position number 3 is going to be encoded like that. And that's a very powerful thing. And we'll see why it's unique. We'll see just now why these are definitely going to be unique. They're never repeating across positions. But for now, I wanted to say that why are we adding? You might have a question. Why are we adding these values to the weights? Like, why is that the correct way of putting them in the neural network? Well, we have to get them into the neural network somehow. And one way to add them, another way to concatenate these values to the weights. The authors of the transformer paper chose to add them, so we're going to stick to that. And we just want to keep things simple. We don't want to add more different components of the neural network that are going to be responsible for the word sequence. We just want to make sure, our job is just to make sure that this information is somehow present, that we somehow are telling the transformer something about these positions. Right now, the way it is, there is no information about the position of the words. Like this, we're adding this information into the network, like literally adding them to the weights. And we don't have to worry about how the transformer is going to use it. But as long as information is there over millions and millions of iterations, the transformer will learn how to adjust these weights in training to account for this information and to account for the position of different words. That's an very important point to understand. Okay, so now moving on to the next slide. Here we've got a chart which looks a little bit scary at the start, but it's actually very useful and simple to understand. So here we've got the embedding dimensions, which are these values over here. So these are basically represent the embedding dimensions. It goes up to 50, it should actually go up to 512. This is for illustration purposes. And here we've got word position. So let's learn how to read this chart. Here we've got position number 1, as we discussed, and it is present over here. So you can see 0, 1, 0, 1, 0, 1, and so on, all the way up to 1. 50 times, but actually it's got to be 512 times. Then we've got position number 2. You can see it here, 0.84, 54, 84, and so on and so on and so on. Position number 3, 0.91, minus 0.42, 0.91, and so on. Position 4, 5, position 10, you can take any position. And you can see that they're always unique. They never overlap. Just based from the visualization that is presented here, you can definitely tell that they're always going to be unique. And that is effectively proof that the transformer will have now access to these encodings of different positions that never overlap, are never confusing to the transformer, and always are fixed regardless of the size of the input. So if your input only has 5 sentences, you'll only use the first 5. You have 5 words. If your input has 15 words, you'll use the first 15. And that way the transformer will have a mechanism to know which position which word is in, and through training it will understand how to use that mechanism, and it will make much better sense of the meaning of the different inputs that it's given. Now make sure to check out these videos on the right or the full course in the description to continue your learning, and I look forward to seeing you there.